Welcome to a series of lectures called Glass, Selected Fundamentals, Basic Principles and Background Information. My name is Christian Roos. I'm professor at RWTH Aachen University and head of the chair of Glass and Glass Ceramic. This video series is intended to give background information on selected aspects of glass science and to reinforce the content of the lectures. The videos are not based on the structure and thematic sequence of the lectures, however. This video is about the concept of the fictive temperature. We've learned that the glass transition Tg is a point which is measured under standardized conditions. Let's look at this diagram in which the behavior of a melt with decreasing temperature is plotted against its volume. Starting at the melt with cooling down at the crystallization temperature, or coming from the other side, the melting temperature, the melt starts to crystallize and forms a crystal. The melt is in a thermodynamic equilibrium and the crystal is in a thermodynamic equilibrium. However, if we undercool the melt below the point of the crystallization temperature without crystallization, we reach the status of a metastable equilibrium. We have an undercooled melt. Now decreasing the temperature further and increasing the viscosity further at the glass transition temperature, Tg, the undercooled melt becomes a rigid glass. The glass is no longer in a thermodynamic equilibrium. So, very importantly, we can state the crystal is always in a thermodynamic equilibrium, the respective glass is not. Now, the concept of the fictive temperature applies when the conditions for cooling down a melt and for achieving a glass are not standardized as we have seen for the glass transition Tg. The fictive temperature describes the glass transition if these conditions vary. To understand this better, let's look at this diagram where we have again here the decreasing temperature and on the y-axis a property of the respective melt and glass, for instance the molar volume or the enthalpy. In the first place, there is actually no objection in using the fictive temperature Tf and the glass transition Tg as synonyms. However, if we look more closely at the different concepts, we will understand the differences. Let's assume again a melt that is cooled down, but with different cooling rates. The melt follows the red curve here for a high cooling rate and some curves here for lower cooling rates, and finally the black curve for the lowest cooling rate. The fictive temperature describes the dependence of the glass transition as a function of, in that case here, the cooling rate. It can be understood as the temperature at which the structure is frozen in and at which the structure can no longer follow the decreasing temperature and at which the structure can no longer adapt to the decreasing temperature because the viscosity is so high that molecular or atomic movements can no longer take place. In that case of the high cooling rate, we would end up with this fictive temperature here, and for the low cooling rate, we would end up with this fictive temperature here, which means the structure of these two different classes, one achieved here with a high cooling rate and this fictive temperature, and the other achieved here with a low cooling rate, and this respective fictive temperature will be different. The glasses will have, for instance, different molar volumes and different enthalpies. And it can be seen from this diagram that the higher the cooling rate, the higher the molar volume is, and the lower the cooling rate, the lower molar volume is. This can be easily understood if you consider the structure being faster frozen in at high cooling rate, so the structure cannot follow with any molecular or atomic movement anymore the decreasing temperature. It is frozen in at a higher molar volume compared to a low cooling rate, where the structure has more time to adapt to the decreasing temperature and the increasing viscosity, meaning the volume can decrease more than compared to the high cooling rate. And the same that applies for the molar volume also applies for the enthalpy. So we can directly see that a glass that is frozen in at a higher fictive temperature, so with a higher cooling rate, has a higher enthalpy compared to a glass that is frozen in at a lower cooling rate with a lower fictive temperature. In a crystal, the current temperature of the crystal itself always corresponds to its structure. But in a glass, the current temperature of the glass generally does not reflect its structure because the structure has been frozen in at higher temperatures compared to the temperature at which the glass is, for instance, used. We can therefore summarize that the glass transition is a temperature at which a viscosity of 10 to the power of 12 Pascal second is reached under very standardized conditions. The fictive temperature, on the other hand, determines the glass transition if these standardized conditions do not apply. And with the concept of the fictive temperature, one has a measure of the molecular order and the structure of a glass. However, it also has to be said that if the heating rate is equal to the cooling rate of a glass and the cooling rate is rather low, the differences between the glass transition Tg and the fictive temperature Tf will be very minor, and basically the fictive temperature Tf equals the glass transition Tg. Last but not least, I would like to mention some methods to determine the fictive temperature. This is more a topic for an in-depth lecture, but I just want to shortly present one possibility to determine the fictive temperature after a Moynihan, in which the heat capacity curve is utilized to match the integrals of a theoretical and a measured CP curve. And by equalizing these two integrals, one can calculate the fictive temperature. Last but not least, it should be stated that the fictive temperature indeed has influences on the macroscopic properties of a glass. For instance, as we can see here, on the hardness, which decreases with increasing fictive temperature, or the Young's modulus, which also decreases with increasing fictive temperature. With that, we are at the end of this video, and I trust it was helpful for your further understanding of glass science.